Do you not know why it doesn't like that on this case? Okay, so do you care if we don't go into presentation mode?
I don't think we're in.
Okay, excellent. I don't know. I'll have to figure out what's going on there, but not today.
Then you're not going to worry so much.
So I think we've got two more people.
But just because this is what the standard is, doesn't mean it's
So one is sick.
Yes.
There are 8 people.
This is for broad.
So we're counting 6, so yeah, there should be eight people here. There are 9 in the class.
You're welcome.
So the idea is that I don't expect people to really have the notion of critiques down for the first several. And then after the feedback on the first, say, 3, people should probably have an idea of how to do critiques. My expectation, or rather, what I've noticed is that the biggest problem people have so far, which is pretty consistent, is that people are summarizing instead of presenting strengths and weaknesses, or summarizing instead of doing analyses. This is pretty consistent. So I think it's something everybody can work on. Oh, yes. Okay. Anybody know if Tyler's going to be here as well? Any clue?
I haven't seen him today in the lab,
Okay.
which is the sign that he might not come.
Okay. Let's go ahead and get started, I guess. Sure.
Okay, so the paper I'm presenting on today is called Efficient Mutation Analysis by Propagating and Partitioning Infected Execution States. And the authors are listed there. So to start off, we'll just quickly talk about mutation analysis. So mutation analysis is just a form of testing, and it's used to analyze the testing software or the testing suite and the relative strength of it. It's known for having poor scalability and really high running times because of the way mutation analysis works, and we'll get deeper into that later on. And 3 things, just quickly, we'll go over this again. One thing that is really necessary for mutation analysis is the ideas of RIP, or these 3 things here. Reachability, to make sure the code is actually reachable and actually executed. Infection, we need to make sure that the mutated code actually infects the code and does something different. And propagation, where the code is actually executed throughout the code and it actually propagates down so that we see a different result at the end. So mutation analysis, we'll just quickly go over 2 terms that were used in the paper and used in mutation analysis in general. The first thing is equivalent mutants, and these are mutants that are syntactically different but are semantically identical to the original test. So an example of this might be, say you have a variable, A, and usually it's set to, say, 0. But in your test case, let's say the mutation analysis changes it to a negative number, say -1. But then implicitly there might be something like, for example, in one of the things I ran mutation analysis on, anything set to a negative number actually got set back to 0. But these aren't necessarily clear unless you look deeper into the code. So it's very possible you're running the exact same code you were before, but you had replaced something anyways, but it still came with the same result because it ended up running the same code, even though you replaced something. So the next one is test equivalent mutants, and that's just a more formal definition of it, as well as it makes this problem more solvable because the above problem when you're trying to look for all the equivalent mutants is just technically intractable, near impossible, just because of how difficult it is to make sure that what you're doing is actually different from what you were originally doing in the first case. So for a test equivalent mutant, a mutant is test equivalent for some test T or T equivalent if the test T cannot detect a mutant. So I can't tell whether it's a mutant or not. So it might be mutated, but it still does the exact same thing.
Okay, so in order to detect equivalent mutants, that's saying that the two programs, remember mutation testing is, or mutation analysis is the idea that we're making several different versions of our program and running the test suite on each of them. Remember that from our introduction? So in order to detect equivalent mutants, we have to prove that the mutated version is going to behave exactly the same as the original version. And proving that two programs are equivalent is in general impossible. It's actually provably impossible. Yeah.
I have a follow-up question. What if our mutation affects unreachable code? Would that mean that the programs will be identical, equivalent?
That would, if that code is guaranteed by the semantics of the program to be unreachable, then yes, those two versions of the program would be semantically equivalent. Because you'd be making a syntactic change, but it could not ever have an impact on the behavior of the program.
Okay.
How did these two differ? What's the difference between equivalent and test equivalent?
The first one is for all of the tests, for all of the possible tests, but the second one is just for 1%. The first one is impossible to connect these two.
Sure. So the first one is looking at, maybe even not the tests, but looking at all possible inputs ever. Look at it that way. Are the two programs, in theory, meaningfully equivalent? Versus the second one is just saying, for a particular input, do they behave the same way?
I have a question. Let's say we have a program that calculates factorial. And factorial of a number n. There are hundreds of ways to implement this function.
Sure.
Would they all be equivalent in a sense?
If all of them
Like,
produce the same meaningful values for factorial, they would be semantically equivalent, yes. Their behavior, their observable behavior would be guaranteed to be the same, right? And that's why it's so hard. There are so many different versions, and proving that one program that computes something using a different algorithm even is the same as another is a very hard problem, impossible in general.
and all sorting algorithms will be in a sense equivalent?
In theory. Now, mutation testing is simpler than that, right? We don't usually replace one algorithm with another.
Yes.
We're looking at small syntactic changes, which is how it's a little bit more practical.
So next up, we're just going to quickly go over the goals of the paper. The first thing is to reduce the running time of mutation testing, because if any of you have ever done mutation testing, because I personally have, there are times where it just runs, because it needs to do prepasses, it needs to generate all the mutants, and then it needs to execute the program on all the mutants. So it's possible in a bigger test suite to say run for 20 or so hours, and then you might have to do it repeatedly just to get a more like.
So regarding this, isn't that task is embarrassingly parallel in the sense that once you get the mutants, you can all of them run in parallel in a sense?
Yes, it is also embarrassingly massive. So,
Okay.
how does this work? If you think about the nature of these mutants, for every single statement of your program, it is made up of numerous expressions. Every single one of those expressions can be mutated in several ways, and you have to consider all of them, and then run the test suite on every one of those mutations. So that's why it's, yes, it's embarrassingly parallel, meaning that you could run every mutant on every test suite independently on its own machine or what have you, virtual machine, whatever. But this still doesn't solve the issue just because there are so many.
Okay.
But if you're running the test on all the different mutants, I mean, you're running the prepasses on every one of the tests, and so.
Well, so far we haven't considered prepasses.
Yes.
In general, mutation testing is just that problem of run every mutant on all of the tests. Run every mutant on the entire test suite. So the number of tests, or the problematic scale here is number of mutants, n, times the number of tests, n. And that's just huge.
But if you're running on all of them, even in this paper, it says that like, after you run, then you decide which test is similar to some other test, and you're throwing away tests.
That's the goal of this paper. That's what we're getting to. That's not
But
a
then, again, you're testing everything beforehand.
Not exactly. We'll get to that. That's one of the things I actually want to talk about. That's understanding that relationship is good. The fact that you're recognizing there's a relationship there is good. We'll get to the subtleties of why you're not exactly doing that once we talk about the paper.
Sure.
So another one is just lower the amount of mutants tested by partitioning the mutants, because like you said earlier, when we look through the paper, we'll see how we partition the mutants that give the same results. So we don't need to run every single mutant, because that's one of the biggest hampering points of mutation testing, is running every single mutant that you generate. And then also it provides some new optimizations, and these ones are just listed here. So all test equivalent tests are ignored. So any of the tests that are the exact same are basically ignored because they don't make a difference, and we'll talk about what that means later.
I think you might need test equivalent mutants.
Yes, I think test
Okay.
equivalent mutants.
Awesome.
And they may also still occur in the local state, but where it infects the local state. But if it doesn't propagate, we ignore that as well, because we don't need to run it, because we know it doesn't affect the overall running of our program. It doesn't change from what we were expecting to begin with.
Is it only the program or the expression?
We'll get to that.
Yeah,
That's the core of your question, though.
Yeah. And then we don't need to run multiple mutants that lead to the same infected state, because it does the exact same thing. So in terms of contributions, it provides a method to detect any test equivalent mutants by monitoring the infected execution states. Again, something we'll talk about later on. It also detects test equivalent mutants by monitoring the propagation of infected execution states in compounded expressions, so making sure it kind of goes down so that it actually has propagation. And then it also has a method to reduce the number of test executions by partitioning. And it evaluates it over 14 open source programs for its testing. So when it comes to propagating and partitioning the infected execution states, tests that detect a mutant must fulfill the following. So mutants must be executed, so they must be covered. They also must infect the state, so they have to give a different value than what you'd expect in that specific state or statement. And then the infected state must propagate, so it must show up in our final execution so that we know that there's actually a difference in what we did.
But what does it mean if you don't have those?
So if you don't have, for example, propagation, it wouldn't matter because you don't need to run it because it doesn't change the overall end state of the program. Therefore, your mutant is just the same. It makes no difference because it might not do anything. For example, and another example is if it's not covered and it's never executed, then it doesn't really matter because it's just dead code. You don't really look at it.
Is that necessarily true?
Sorry.
The first one?
Yeah. Here's a subtle issue. So there are things that that are not covered that could potentially be covered by something that's not in the test suite. And there's a difference between those two. If something cannot possibly be covered, then it's guaranteed to be dead code. If something could be covered but is not,
In the test suite.
then you just don't know. So it's just not detected. So there's ambiguity there. And if things don't infect the state, what does that mean? So it's covered, but you don't infect the state?
There's nothing changes.
Nothing changes, so it's equivalent. You haven't actually introduced a bug to detect at all. Yeah.
So, like we said, the things we talked about, reachability, infection, and propagation, are key to this paper and key to mutation testing in general. So, I don't think I need to recap it. We've said it a lot of times. We just need to make sure the code is actually reachable to some degree by our test suite. And also, infection, it needs to be infected, or else it's just equivalent. And propagation, we need to make sure it differs from what we expect as our final result. So the way they do the optimization is they use some pre-pass approach, and they first determine whether the mutated expression would compute a result in that expression that's different. So we would call this the infected execution state, because it would infect the execution and what we would expect to see in that local area. And then also using the pre-pass approach above, it also sees if we get a different result compared to the test oracle, what they called it in the paper. Just making sure that it's different from, it propagates down, such that it's not just the local state that's infected, but also the overall program. So you'll see it in your results, and it's different from what you were expecting.
Okay.
Is it really what we see?
There's some debate there, yeah.
Because
Propagation does not propagate down. It comes off after the next statements.
it only figures out if it comes out of the enclosing statements.
Right, so there's some subtleties in what they're doing with this propagation. And we'll see this when you dive into the actual, so right now this is still a bit more high level. You're gonna dive into the actual examples. That's a good question. There's a difference between propagating to the output and propagating to some other point within the program. These are different granularities at which you're checking propagation, and they reflect certain approximations that may have costs and may have benefits that we should consider. So for now, at least, I think we can move on from that. We'll come back to this again.
Sure. Yeah, it's later on. And lastly, with also the same pre-pass approach, we'll check whether they lead to the same overall result, which is one of the things they talked about.
So what you can see here is that there's a notion of this pre-pass, which should be a single execution that gathers information ahead of time. That lets us do stuff that's more interesting. So you're doing a little bit of extra work up front with this pre-computation.
To save the work afterwards.
Right.
Yeah. So you don't have to run every single meeting. So first up, the infected execution state. So a test infects the execution state of a mutated expression if the value differs from the value in the original expression in at least one evaluation, and the formal definition is there. And we'll go over it later on when I look into the results and into the paper, and we'll go more into the exact formulas and how they work.
So we might want to visit this a little bit, because it will come back, so we could do it now and maybe get it out of the way. So this is a bit more formal, and this is one of the first times we've seen something that's a bit more formal, I think, right? In terms of how it expressed what was going on. I don't think our previous papers did this. Can anybody read that?
Like the TB test of evaluates.
Okay.
This basically says that if the expression you're executing in a test suite, and if the expression, the mutated expression, if at any point they're not equal, that's what you call it.
Okay, and you said at any point for a certain reason, right?
So that's because it's executed n times. I mean, an expression can be repeated in a test, right?
Yeah, exactly. So an expression could be repeated in the tests, and they're just saying that if the results of your mutation, results of the original, ever differ, then that denotes infection. If they ever differ, for any one of these many executions, for instances.
So next up is a small aside on side effects. We just assume that every test that may infect its execution state every test may infect its execution state when there's a change side effect. So one of the examples I listed here was basically the original. If x greater than y becomes mutated to if x greater than or equal to y, it doesn't change the side effect. And same with number 2, but number 3 does, because it replaces the whole expression with true instead, if true, instead of a comparative.
So why is that guaranteed to have a side effect?
What exactly is the side effect?
Yeah.
A side effect means that you are you know that you're altering the meaning of the program, really.
But then you're altering every time you're changing something.
Not necessarily. So remember, we're looking for things that are test sensitive, things that are test equivalent.
But if you don't alter, then it becomes test equivalent.
Well, so let's say that x is 5 and y is 3.
Okay.
And we change x is greater than 3 to x is greater than or equal to 3. Was there a change?
So is it test case dependent?
It is a little bit. So you can see that for things that are based on the values, it's very much test case dependent. For other things, you can see as well that if we're changing the structure of the program, right? If you change it so that there's no longer a false branch in an if statement, you're changing the set of possible behaviors in a very real way. You know, there's no way to take a false branch anymore. So you're changing the meaning. So that's a very real side effect. Because anything that would have taken the false branch is now guaranteed to go along the other direction. Guaranteed. If you look at 4, there's a side effect there as well. Right?
I'm actually a little confused by the form when I was looking through the
Yeah.
example.
I'm not surprised why. When we talk about the implementation, we'll see why 4 is the way it is. There's something that happens inside 4, which I say makes it not just an expression, but in spirit a statement within an expression. And because they only track things to the boundaries of statements, they are forced to treat that as if it has a side effect. What happens in 4 that doesn't happen in the others?
Because we don't know y plus plus when it will be calculated.
We're adding we're adding a definition, right? If you look at the original, we're not redefining a variable.
Okay.
If we're looking at the mutated one, we are redefining a variable. The fact that we're redefining something that wasn't redefined before means that the way in which they optimize things would no longer work. Essentially, what they're checking for is corner cases that would prevent their optimizations from working. They call them side effects. It's a little, there are other notions of side effects that are much better defined and much clearer. I don't think calling these side effects is the best approach that they could have used here. All they're finding here are corner cases that would prevent their system from working. And so they say, in these cases, we throw our hands up and we'll just test those anyway. That's it.
We don't do anything.
So next up, propagating the infected execution state. An infected execution state propagates to an enclosing expression if it leads to an infected execution state in the enclosing expression. So basically it's just saying that if there's something local, say you change, I don't know, x plus y greater than some other z, and you change it to maybe less than or equal to, and if that changes the result in that enclosing statement, then that itself is infected as well. Because it's not just what was changed that's infected, but the whole statement.
So I think it might be clearer if, with x plus y greater than z,
Yeah.
if x plus y gets mutated,
Yes.
and that affects the result of the greater than,
Yeah.
then it propagates out. Yeah.
There's a formal definition of it again. That's fine. That was
Yeah.
a little.
Yeah, this one is intriguing in part just because there's so many ellipses. But if you ignore that and read the text, it's far clearer.
Yeah.
They do a fair bit of formalization, which is good in terms of clearly specifying what they're doing. I think it also adds to the publishability insofar as it makes things seem it makes things seem more rigorous. But the text itself was actually enough. in my opinion.
That's it.
This is a concern. One of the things that you'll see, I think, when we discuss how you could implement this as well, is that the underlying idea is very simple. They presented it masterfully. And this is a real concern when you're looking at how to write papers.
And then one of the examples I gave for propagating the infected execution state with test equivalent and the infected state. So the first one would still be a test equivalent because it doesn't change in the enclosing expression. It's still false in both sides, while at the bottom it would change from true to false. So therefore, not only is this infected, but the whole execution state propagates down or out.
So I have a question there.
Mhm.
Like he talks mostly about Boolean values.
Mhm.
Like you make some changes and the false remains false.
Mhm.
If you're talking about integer expressions and you change some value, it is surely to change expression.
Not necessarily. Can anybody think of an example?
Arithmetic and it won't change.
Right.
Test dependent one. It's like you change plus to minus, but you all second operand is always zero. In the
Yep.
test
Yes,
case.
was that one case, right?
That happens.
No, I-
Every little bit helps.
Or you
Yeah.
multiply by zero, like somewhere,
Mhm.
and then no matter whether it's plus one or minus one, you multiply by zero. Yes, one
Yep.
effect.
Yep. And there's also an interesting aspect that a lot of the values that you end up computing inside a program are solely used to make decisions, which means their impact is going to be on that condition, and they may not be printed out anywhere else. So you mutate them. If you can find out that they're equivalent with respect to the condition, you throw them away. There's a good chance you're going to have high impact.
So moving on, partitioning infected execution states. For this part, it just says that mutants that lead to the same test result, not overall, I guess. Test results, they're just partitioned together. So they're separated together, and we'll go more into it a bit later too, in the actual, how they implement it. Actually a little confusing. So that's just a formal definition again, talking about how it partitions if they have the same mutant result. I'm not gonna, I can barely read. And
We can try to go through it.
Yeah.
I mean, I'm not sure if it's of too much value, but it's great for publishing book. I mean, it really just does what they said in English. So intuitively, you could say that if two different mutations result in the same value within an expression, their impact throughout the rest of the program is going to be equivalent as well, right? It's going to be completely the same because they made the same equivalent change, and that's all they're stating here. That's all they're stating here. Just based on identifying representatives inside a particular partition P. Yeah.
So that's just one of the examples they gave. It's just a simple example how they partition things like A multiplied by B if they're both 1, or if they divide by B, and it's just the exact same, and how they form the partitions. So implementation using major, this is just the 4 phases that they talk about. It just so first off, in the first phase, major just instruments the program under test to measure coverage. So it just checks how much of the code is actually covered. And then major also links in a runtime library to support instrumentation. Basically exactly what it says on the paper. So phase 2, major then runs the program's test suite on the instrumented program to determine which of the mutants are uncovered by which tests and are test equivalent. And then in the third phase, they start with the original version of the program. Major then inserts in all the possible mutants into a single version of the program, and each mutant is disabled by default. And then major, and then the fourth one is just mutation analysis by running the test suite on the mutated program, and it activates each mutant one at a time. So it basically just does an execution for every single mutant that they generated in the previous 3 phases. So the first thing it goes over in the paper when it talks about implementation is the prepass and how it instruments it. So in the first phase, Major would instruments the original program by replacing every expression that can be mutated with a functionally equivalent method. And there's a bunch of ways they do that. They replace variables sometimes, they replace expressions, they do just about anything you could do to your code. They can basically.
So the nice thing here is that you can abstract away whatever changes you want to make inside this eval function that they've got. So you can do this transformation once and make it behave however you want by linking in different libraries to define the behavior of eval. It's a little bit crazy.
I have a question. So, aren't we discussed before that it's hard to make tests that they will do 100% test coverage?
Yes. Yes.
So, we always have some lines of code that are not covered by our test, and therefore, even if theoretically if we do perform this mutation testing, it won't be catched.
So what this does is identify those.
Okay.
So this isn't this is mutation analysis as opposed to mutation testing. So they're not trying to generate tests. They're trying to say, given a test suite, how good is it? What aren't we testing?
Okay. Good.
And then just the part about it, expressions and mutations. This is just taken directly from the paper. And then there's just an example of the expressions and then the mutations. I don't really know why they have to.
But they're just being explicit. Whenever you see a research paper, it's pretty good if they're explicit about what's going on, just so you get a clear idea. So what is this telling you? Well, it's telling you what that instrumentation does, right? I mean, you see this eval 5, eval C stuff that they had on the previous example. This is just saying what that was.
Okay.
Because if you leave it ambiguous, then it's up to whoever's reading it to try and figure out what it's actually saying. And again, that will decrease your, one, it decreases the precision of what you're presenting. And as a result, it decreases the scientific value and decreases the publishability.
So then it talks about monitoring the infected execution state. So in the second phase, Major executes the test suite on the instrumented version of the original program and determines the set of T-equivalent mutants that do not need to be executed in the fourth phase. And then it also talks about how the eval method of the runtime library determines for each test and each mutation which ones have actually infected the state. So it basically just monitors and checks if it's infected the state.
So that eval then knows what the original behavior was, knows what all the mutants do, and can just keep track. Basically do the entire analysis. Nice.
And then propagation. So during the prepass in phase 2, the runtime library also keeps track of the propagation of the infected execution state using mapping. And any mutant that has an infected execution state that doesn't propagate any further is removed from the mapping, so we don't need to run it later. And this is just the example they give in terms of the propagation, and whether it goes down in the next state and how it does.
So can you go back one slide? Okay, yeah. So when we see any mutant that has an infected execution state that doesn't further propagate, it's removed.
That's what I think I got.
They say it's removed from the mapping. What mapping are they referring to?
First one?
Okay, so this is just, in general, they've got this tracking of which values and which mutants created those values that they're always maintaining. And so if you have something that is equivalent, essentially, you remove it. Equivalent in some fashion.
You keep only the distinct things in the map, does it?
Sure.
Is it what we're trying to say?
Yeah. This is a pattern, though. This is a pattern that we should remember when we look at the next thing.
So then, for partitioning, all the mutants that have the same infected execution states are grouped together in partitions. And each time a test T executes a mutated expression, the partitioned cells are updated so that each cell contains all the mutations that evaluated identically with the rest of the test. So basically, it's just saying anything that gives the same result in that test is just put into the same partition, from what I understand.
Which is exactly what we did for the infected stuff too, kind of. Just keeping track of which things behave the same as others. It's the same thing. They just get two distinct bullet points in their contributions for the same implementation. That's cute. That's another wonderful thing for formalizing the problem well and publishability. Same implementation, two contributions.
And then each mutation that was not monitored is then added with a partition of size 1. And then the last thing is just the runtime library picks an arbitrary representative mutant for each of the partition cells. And I was wondering, because it doesn't really seem to go over in the paper, does it just pick the first one? Does it even
That's what I
matter?
do. Yeah. So you're making this map, right, of the values essentially that are going through this. Or the way that I would do this is actually the inverse of what they did. They had this map from IDs to values, the mutant IDs to values. I would switch it around and have values to mutant IDs. And then you just check whether or not you've seen this value before. And it automatically does all of this reduction for you. So, yeah. Yeah, that. Yes,
Yeah,
in
okay.
answer to this. That means you'd only add the first one to really bother flowing it through. All the others would just be automatic, basically.
So just basically what it does here, and it's just one of the examples they gave in the paper for how they partition the different tests and the representatives of them, and whether they're executed or not. So I'll just quickly look at the results in the paper. Actually, do you have a copy of the paper on?
That's. I think if you look at Firefox, you'll see our schedule. Okay, you want to see our schedule, right? Well, yes. The other thing that you might have seen there is actually the fact that LLVM now has a fuzzer built in that was just committed a few days ago, which means if you wanted to generate random C programs using just LLVM, you could do that too, in case anybody's still interested in that. Total aside, but interesting. Okay, yeah.
So, because we did this for the last
Can you press F11?
Yeah. Does it work?
We can find out.
Yeah, it works.
Hey, all right.
So the first table here is, or the second table, or the first table we'll look at is just the test suites that they looked at and what they did for their study. So they did 4 different types of testing on it. There's a manual, random, a branch, and a week, and they talked about what it was.
By manual, they mean the test suite that the developers have written.
Yeah, so manual is the set of tests that came with the program.
Like I said, my question was, can you trust them?
So we'll get to that. When we look at the table that's just a little bit lower down, we'll ask exactly that question. The other 3 test suites that they use for each program are automatically generated, right, by a test suite generator. Well, we mentioned that was one of these problems that's out there, test suite generation. What they used was a system called EvoSuite, which essentially uses genetic algorithms to evolve a test suite randomly, but with the genetic constraints targeting those different criteria that they list, right? The criteria of just random, so a random test suite, just completely random, just given that you have a certain number of tests. One that targets branch coverage, we talked about branch coverage, so everybody remembers what that is. And one that targets weak mutation testing, which is basically targeting infection.
The propagation doesn't happen?
it doesn't try to have propagation, because that's tough to reason about. It just tries to make sure that you hit infection.
Could you talk about the columns of this table? Because it is
Mhm.
kind of weird, for example, especially for the column time. So at the top of the table, it explains that it is the time that takes for executing all the tests on the program.
Mhm.
But also on the previous page, it says that it says something else. It says it's the overall time for mutation analysis and the pre-test execution.
Right. So there are a few things in there. One is the inclusion of their optimizations, which is the pre-pass and then the resulting time using the information they get from that.
Yeah.
And the other is just without their optimizations, without any of their optimizations. And so those are the things that we want to consider. For these are the baseline results.
But
So-
in both, it says in table 2, but, but in table 2, there's only one column time, so it's confusing what it
Right.
actually refers to.
I believe table 2 is all just baseline results, which means that it doesn't include any of their optimizations. It's just the
Yeah.
baseline, you have this many mutants, you've got this many tests.
Yeah, so it's like a mistake in here because they mentioned this.
Yeah, it would be, yeah, lack of clarity, certainly.
There is an optimization in this.
Coverage,
The
yes.
coverage,
Yeah, yes, so coverage is the standard one that exists prior to their work entirely.
It means the pre-pass, as they mentioned.
Oh, that's true, It needs one, yes, that's absolutely true. So I guess there is the standard pre-pass, just to determine the coverage. Yeah, that makes sense. They still just give the one overall time, just because this is their baseline result.
So I'm wondering, like, we were talking about that mutation analysis takes a lot of time, right?
Right.
But the time we see in this table are not that, they are in seconds, right?
They shouldn't be in seconds, no.
They are
That would be very surprising.
Like say the,
It says in
the
the,
first line
yeah,
takes
Takes
9
time to
seconds to
second.
run.
That's
10 seconds to run on the instrument
that's
program.
crazy.
yeah, and also it has another problem.
But isn't that just one execution of it? Isn't it?
No, it says it's like running whole test.
Oh, you're absolutely right. So if we look at the bars, the bars that are between test suites and the bars that look at mutation analysis, this is just the time for the test suite. Sorry. Yeah.
So then you have to multiply it by the number.
Yeah, right. You have to multiply it by the number of actual mutants.
So for each of the generated mutants, it would require factoring.
Right.
I'd assume the execution multiply the time by the
Is that
execution.
weird? Because if we change it, the time will change as well.
If we change what, the time will change as well.
You say the mutants, for each mutant, the time execution cannot be the same, right?
Well, so this is not the mutants yet.
Yeah.
So what's happening?
That's just the baseline time for the test suite. You run the test suite once.
Mm-hmm.
On the uninstrumented.
Yeah,
on the original program.
actually.
That's what this number is. Yeah. You have to. It would be nice if they had a vertical bar.
Yeah.
They do not. So this is the time for the test suite. The horizontal bar above time shows that this is the time for the test suite, and it has nothing to do with the mutation yet.
Yeah. Okay.
So it's just the time for the test suite. Yeah, that's So I've read this paper before, and it made perfect sense to me then, and I didn't remember that. I think that could have been presented a little bit clearly. Yeah, there are some trade-offs with the vertical bars making things messier, but I think it would have aided in terms of the clarity there. Yeah.
Oh, also, I have another question. So it says in the columns we have this execution thing that they didn't explain what it is exactly. So, and it's like 12,000, right?
No, that's the
Uh-huh.
number of
What is this exactly?
test executions, I believe.
Just execution?
Or
But then-
maybe executions of the
So it
test
says
suites.
executions show the
Subset.
number of test executions necessary for the mutation analysis.
Yeah.
When using
Yeah.
only the mutation coverage operator, that's this.
Yeah. So that's the number of tests they ran.
That's the number of tests they would need to run for the
For
mutation
me?
analysis.
Yeah.
So for every single mutant, for the ones that are covered, the
Yeah.
ones that they would need to run,
Yeah.
that's how many executions. And I'm
Multiplied
guessing the
by time?
upper bound would be multiply that by the time in seconds.
But then the point is, we have like 1,000 tests, and we only execute 12,000 executions. It means like for each test case, we are doing like 10 executions almost.
That would be very surprising, yeah.
And also in the table 1, they say that the number of mutants is like 11,000. So
Yeah, this makes me think it's test suite executions, it must be. Not test executions, but test suite executions.
so we are not covering any information about the mutations yet, right?
Right, none of their optimizations.
Yeah.
Okay.
Yeah, that is a bit funky. Yeah.
You need that numbers?
I wouldn't say so. Let's look at table 3 though, because we're running out of time.
Okay, so table 3, this is the mutants that remain after the pretest. This is just the ratio of the non-filtered mutants left after the optimizations that they do compared to the number of covered mutants.
Yeah.
So we can see in the last one, it actually drops the number of remaining mutants by quite a bit. Especially for random, but I think it's just because they were lucky on that random.
Well, it turns out that in general, randomly generated test suites are not as good as test suites that have some directness to their criteria. Because if you've got a test suite that is randomly generated, you're less likely to make sure that it has, say, branch coverage even, which is weaker than weak mutation coverage. And you might notice, this gets to your question, that weak mutation coverage, even though it is still reduced a lot, it's reduced more than manual, which means that the manually created tests are the strongest. They're the best tests.
You can trust the developers. You can trust the developers.
Yes, because the developers know what the program is supposed to be doing, basically. In general, this is true. Okay.
Yeah. So, so in the results section, they also talk about, they had 4 questions that they wanted to answer. So the first one was just talking about coverage without the state infection. Here. And then there's some tables in this one.
Yeah.
And
Which
then
is informative.
Yeah, it is important. And then in table 4, it just looks at the benefit of infections, and then it just breaks it down by project and how the infection changed.
Since we're running a
Yeah.
little bit well past time.
The last table then.
Right. Well, if we look at each of those, though, just the summary is every single one of the optimizations has a benefit, and even when you combine them together, you get you get synergistic benefits.
Yeah, basically, the last part is just where it looks at the 4 different things that they did for their test and how that benefited the overall test in terms of the manual ones, the generated ones for random, the branch ones, and the weak ones.
Yeah.
And we can see noticeable improvements in almost all of them in terms of runtime and executions on average, just because it basically removes a lot of the mutants that weren't necessary to run in the first place.
So they managed to reduce the runtime by about 40%, is their final conclusion. Any issues? Any issues? I mean, we have to get kicked out of the room, I guess, but anybody have some comments or problems or anything about this paper that they want to go through?
I think they didn't present the actual number, so it's kind of weird, like the actual number of the runtime.
Yeah.
They only said that it reduced by 40%. So for me, that I don't know, like, what is the order, I'm like,
Sure.
well, how is it working?
It gives you a notion of the relative behavior. It doesn't tell you what the usability of their tool is.
They didn't talk about scalability. They didn't talk about scalability. How does that affect?
I think this gets to scalability, right? because they are talking about how much faster they are and how many tests they remove. That is exactly the scalability issue, I think, when you come down to it. But
Okay, I had a question, like, in the pre-pass, they're testing every test mutation, they're passing over all the tests, right?
right.
So, and then they're removing certain tests and they're running the less test cases again.
So this is glossed over, I guess. But this is what's interesting about, one of the things that's interesting about the paper is that they only consider every single mutant on a per statement basis. So you're only executing a statement of that mutant before you continue on. And that's much better than executing the whole test, right? So that's how they get the benefit. They execute a statement of every mutant to see if they just got this very localized propagation.
Okay.
And based on that heuristic alone, they're able to trim out 40%. There's a lot of stuff going on there. There's some very interesting papers that I think can be written that further some of those results that maybe I won't talk about on camera. But I think that
Oh, you can stop it.
well, we're out of time anyway. But I think that is one of the interesting issues. You know, what are the trade-offs there? They're looking at one statement. How far can you take that? Something? Yeah, anyway, that's all we have time for.
I feel like my conclusion after reading this paper is still mutation testing still takes too long. Even when
It does. I agree with you, and your experiences reinforce that, right? I mean, you've used the framework.